All good and not blurry. Excellent. And it's 10:10. So we will begin. Will is here to help answer questions. And this is Data 8, lecture number 4. Announcements. Homework 1 is due. Actually today. Well, tomorrow technically. So it's totally fine if you turn it in tomorrow. But you might as well get a little bit of extra credit by turning it in today. The reason we have this extra credit is just to encourage people to start their assignments earlier than they normally would, and it works pretty well. So most students end up turning it in on Wednesday, which is excellent. Probably you've looked at it already since it's Wednesday. If you haven't, let's take a glance now. It's not that short of a homework, and you can't imagine how we have so much homework given that we've only had a few lectures. But we're just trying to get you to start thinking about making conclusions using numerical information, which is much of what data science is about. I wanted to give you a quick tip about what kind of collaboration is fine by me. You're allowed to discuss these problems, even discuss how to answer them with each other. In fact, I would encourage you to do that. So for question 1, which I suspect you've read, it says over 25% of home burglaries occur between Memorial Day and Labor Day. Does that support the claim that burglars are more likely to go to work during that time? There's a numerical part to this, the 25%, and usually the number that's involved in the question is actually important. If you were collaborating with somebody else and you weren't quite sure how to get started, you might say, well, the thing I noticed is that this is 25% of all burglaries. I wonder what fraction of the year occurs between Memorial Day and Labor Day. And then there's a hint about that. Oh, Memorial Day is the end of May. Labor Day is the beginning of September. So you got June, July, and August in between, 3 months plus a little bit. What fraction is that? Well, about 25%. It's okay to discuss this kind of thing. Now, of course, you might want to try to solve the problem on your own and figure out the fact that you're comparing something that's 25% to something that's about 25%. But if you get stuck, it's totally fine to talk to other people, and you can help other people as well. Just don't tell them, oh, here's what I wrote, and send them your answer. Instead, talk to them about kind of the key insights and let them synthesize it themselves. I think that's a more productive way for everybody to learn. Few questions. For open-ended questions, is there some leeway about what is considered correct? This is a question, for example, number 1, where it asks you, do the data support the ad or not? You do need to decide. We're not going to give you credit if you say, sometimes yes, sometimes no. Just say, yes, it does, or no, it doesn't, and then give an explanation. There is, of course, some leeway in exactly how you explain your answer. But if you don't point out the key piece of information that led you to decide yes or no, then you probably won't get credit. So your goal is to be succinct, but take a stand if it's a true-false question or whatever. Say what you think the answer is, and then write down a sentence that describes why you think that's the case, and then you're done. And yeah, for uploading recordings, we're going to be more efficient about it as time goes on. So yes, hopefully we'll have recordings uploaded the day that the lecture happens. A question was, next week we go back in person. Will lecture be recorded? What's going to happen? We're going to go to the lecture hall and give lecture there, but still run Zoom on our laptops, just like I am right now. And so you'll be able to watch the lecture live via Zoom, or see the Zoom-based recording, or see campus's recording, but it won't look quite as nice, right? Because right now I'm just talking to my phone. And next week, we'll be talking to the audience. So we'll try to make it still effective for people who are watching online. But yeah, but we'll just have to iterate a little bit to make sure it's still effective. But the idea is that this Zoom-based way of watching lecture will be supported throughout the semester. It's just we'll be doing it, recording it, broadcasting from a different place, which is within the lecture hall. And if you'd like to come to the lecture hall, you can. In order to make sure that not too many people come to the lecture hall, we are going to have a sign up. You'll see that come out soon. so that we just don't overload the room, because I don't think the right way to start live instruction is to have more people in the room than will fit. But I actually don't think that's going to happen. It seems like enough students are pretty happy watching the Zoom-based lecture that that's where most people will probably continue to go. Yeah, and that's totally fine with us. But if some of you want to come live, that would be delightful. We'll be there. Someone asked, will 1,600 people fit in the hall? Well, right now we only have 900 people watching this lecture. A lot of people have already switched to video. And yeah, as I said, we'll make sure that we only allow as many people to come as can comfortably sit there. I don't think we're even going to fill every seat, maybe 2/3. Okay, let's get started. Oh, one more announcement, which is that many students benefit from practice. And it's a good idea to practice either on your own or with a friend, or in a small group with a course tutor there to help you and give you suggestions and give you worksheets and example problems to work on. Oh, that sounds great. And it is. And you can have that in this course for free just by signing up on tutoring.data8.org. But I suspect this will fill up as the course becomes kind of more challenging as we introduce more and more concepts. So go ahead and sign up for tutoring. Tutoring will happen in person and starts next week, but you can sign up right now. Attending lecture is not part of your grade in this course. Tutoring does not give you extra credit, it just gives you extra knowledge. Well, not extra knowledge, but extra practice. And that extra practice, you know, it's a good way to do well in the course and get the most out of it. So come to tutoring because you want to learn. And yeah, I think I answered most of these questions. I'll let Will try to capture the rest of them. We talked about basics of Python and what a table is, how to manipulate a table. Now we're going to talk about types of data. We'll spend a little bit of time talking about different kinds of numbers and how they're represented in the computer. And then we're going to talk about a key concept for this course, which is arrays. So even students who have programmed before may not have used arrays, or at least not use them as much as we will in this course. It's a key part of many different programming languages, including Python, whenever you want to do some kind of interesting numerical manipulation, like in data science or in scientific simulations or graphics or artificial intelligence. This concept that we'll learn today is used everywhere. So you might as well learn about it now. But first, I'm going to talk about a little part of last lecture that I skipped because I ran out of time, which is why we introduce names at all using assignment statements. You don't actually need them. It turns out that while complex expressions can be written without any names, just by putting a bunch of numbers and arithmetic together, the result is often difficult to interpret. And so the reason we use names is often to document the meaning of the different quantities that we're combining together using arithmetic. And that makes the equations much easier to understand. So it's useful to choose names that will actually help you understand what you did. Imagine as you're writing your code that you are going to have to read it a year later and you've kind of forgotten what it's all about. Use names that would help remind you what's going on so that you could reinterpret what you've already done. And that means they'll be useful for other people reading it as well. So as a quick example of this, if you know, as of January 1st, the minimum wage in California for companies with a certain number of employees, I think at least 26 employees, is now $15 an hour. So how much is that if you work for a 40-hour week? Well, 15 times 40 is not working. Backup plan. Good thing I have a backup plan. So, you know, you can make $600 a week, or if you work for 52 weeks, you can make $31,000. But, you know, if you go back and look at these numbers a year later, you might not remember what they mean. So instead, it's common in a notebook or in any other programming environment to write down what's going on. So you might have a sentence. And then you might use names in order to describe what these different quantities mean. Then when you compute 40 times 15 by writing hours per week times weeks per year, then of course, you now know that you're computing the hours per year, but you could in fact write that down. And then if you want to know your weekly wages, you could combine your hours per week with your California hourly minimum wage. And you know that these weekly wages aren't just for a particular person, they're for anyone earning the California hourly minimum wage. And then you can compute the yearly wages by combining those quantities. So I just wanted to emphasize that the role of names in programming isn't just in order to be able to do new things with your program, it's also to be able to communicate with your program, to describe what's going on so that somebody can follow the math that you're performing. I see no questions. I will go on. Let's talk about numbers. Some of this we saw last time. We're going to go into a little bit more depth. If I multiply 10 by 3, I get an integer. If I divide 10 by 3, I get what's called a float. And notice something kind of funny happened. It showed me the answer is 3.3 repeating, but instead of writing out 3.3 repeating, it wrote out up to 15 or 16 significant digits, and then it has a 5 at the end, which isn't even right. So maybe I need to get a new computer. No, actually I don't. The computer's fine. The way in which any decimal is recorded or stored within a programming language is a representation that has finite precision, meaning it only stores so many different positions after the decimal point, so many significant figures. And it's always 15 or 16. And why is that? Well, it's a pretty useful amount. In fact, when NASA sends rockets into space, they have to represent pi in order to figure out the curvature of various arcs. They use pi to 15 decimal places to do it, and they still manage to land stuff on the moon and fly by Mars and stuff like that. It's a lot of precision, but it's not infinite. People have worked out pi to many more digits than 15, but those additional digits really just aren't useful for most scientific or data-centric applications. So this constraint, which exists not only in Python, but in most programming languages, is just fine. But it is something you need to be aware of because it can lead to surprising results, like this 5 here at the end. So the two things I want you to take away from this one example here are that when a number is represented, and it's not an integer or whole number, instead it's some fractional thing, it's represented using finite precision of 15 or 16 digits, and the last digit might even be wrong. Now, when you have multiple numbers that all are off by the last digit, and you start adding them together or dividing, you can actually accumulate little errors. If I take this, add it to this, well, actually things got better rather than worse. Now this is, I'd say, correct. But you could imagine that maybe these things come out wrong. Why did it get better instead of worse? Well, there was some very careful thought that went into designing a system that could represent numbers, which in principle should take an infinite amount of memory. If you wanted to store all of pi, or you wanted to store all these 3s forever, then it would take a bigger computer than we have, right? So instead, there was a compromise made, which said, let's keep 15 digits. But very careful work was done to make sure that when you represent numbers in this way, and then you perform arithmetic, add and multiply, you tend to minimize the amount of error that shows up in the last digit. So you really do get the right answer, or something very close to it most of the time. And that means that for most applications, you don't have to think about it because you don't really care about these digits down here. Like 3.33333 is already so close to 10/3 that it's fine for most real applications. And the fact that there might be a mistake way down here just doesn't matter very much. But the fact that it exists is important and something you need to know if you're using programming for manipulating numbers. Okay. There are, in fact, two types of numbers represented, integers and what are called floating point values, or in short, called float. Why are they called floating point values? Well, the point is referring to the decimal point, and the nice thing about this representation called floating point values is that it can represent numbers that are very large and very small, all without using a whole lot of memory on your computer. That's kind of the design, and it's a very clever design. It was, in fact, worked out and formalized by a Berkeley computer scientist, Professor Kahan, and he won a Turing Award, which is like a Nobel Prize for it. And I asked him once, what should I tell first-year data science students about this representation that you think would be useful to them? And he said, well, a simple rule of thumb that works across a huge number of applications is that you want to store twice as many digits of precision as you actually need. And then you can trust the first half, and there might be an error somewhere in the second half. That's super conservative, but it works in lots and lots of different simulations. So yeah, it's true that if you do some huge amount of math, the error might not just be in the last digit. It might even show up elsewhere, but you can really rely on the first half of the digits, and those are usually enough for most applications. Okay. I can raise 10 to the third power. What have I done? I can raise 10 to the half power. I don't remember what that means. That means take the square root. So again, this is a finite precision approximation of the square root of 10. You only get 15 digits. Now, there are cases where you get more than 15 digits, which is the integers. If I make a really big integer, like raise 1, 2, 3, 4, 5, 6, 7 to the 890th power, I get more than 15 digits of precision. I get an exact answer. And this is because in many different applications, it really is important to have exact integers, the exact count of how many times something happened, because you want to know if that's even or odd. And so you need to know whether the last digit is even or odd. These kinds of things come up in real applications. And so in Python, an integer can have an arbitrary size. It's really just the floating point numbers, the decimal expansions, that have this limit of 15 or 16 significant digits. So let's see that part in practice. Why is there a Q in there? I'm just banging on numbers. I typed out this huge number with a lot of digits after the decimal place. And when it was evaluated, it gave me some simplified version because of that limitation I described to you. So here's something that's wrong. If I subtract this number from this number, I should get the digits that remain, the 0.000034, but I don't. Okay, I didn't do anything wrong. And in fact, the computer didn't really do anything wrong. I mean, the math is wrong. But usually when you're subtracting one huge number from another huge number, who cares if they're different way out here in the 8th decimal place? So for almost all practical applications, this is fine. But it is something you have to be aware of, is that when Python read in this number, it actually just recorded this approximation to it. And likewise, when it recorded this number, it recorded the same approximation to it. When you subtract them, you get 0. You can, however, store really small numbers. So for example, you could store 6 divided by 4,000. In fact, you could store 6. Well, what happened there? We got a smaller number. Oh, and it changed format completely. So dividing by 400,000 should give me 0.0000015. That's what this is in scientific notation. So that's actually an exact representation of 6 divided by 400,000. And if I divide it by, something much larger than 400,000, whatever that is, then all of a sudden I get a very small number, 1.5 times 10 to the negative 30th power. And so Python has the capability of recording something very small. It just only records 2 significant digits of the representation. Okay, I've said a lot. Let's see if there's any questions I need to answer. The question is the error called a floating point number? No, it's really the representation of the number itself that's called a floating point number. And it's a fact about floating point numbers is that they have limited finite precision of 15 or 16 digits, and you can't get them to record more digits after that. And another question is, what about calculators? Do they have this problem? And they do. Yeah, they, in fact, basically all programming languages use the same representation of floating point numbers. That makes different programs and different computers able to interoperate very easily. So they all use the same standard, the IEEE 754 standard, which is how you represent numbers in a computer. True of calculators too. And so maybe you never knew you had this limitation, but you did. And the question is, does this issue, like subtracting and getting the wrong answer, only happen during subtraction? Great question, but it's not only during subtraction. Let's see if I can come up with another example. What's the square root of 13? 3.6055 something. So if I square that, I should get 13, but I don't. Get something really close. So it's fine. That's basically 13. But because this was a finite approximation to the square root of 13, it happened to be that when you multiply that by that, you didn't actually get 13 back. You got something very close. All right. I showed you that you can get really small numbers. And it should be the case that if you multiply this really small number by a really big number, like 1.5 to the 30th, you get 6 divided by 4. What have I done? No, let's do something else. That was a confusing example. Here's some really small number, which was 6 divided by something huge. Well, what if we then multiply by that something huge? We should just get 6 back, right? And we do. So I would think of this as like very reliable, except for every once in a while you get like something a little bit wrong in the final decimal place. And even this subtraction example that I showed you is really just getting something a little bit wrong in the final decimal place. Like when you have this much, who cares whether you're off by a little bit way down here? Well, we better not, because there's no way to represent that part way back there. One question was, how can we have many decimal places for 10 divided by 3, but only a few for cell 15, which I guess has disappeared. But I'm guessing maybe it was this one. This only shows 2 decimal places because the rest is 0. And if that didn't answer your question, I'm sorry. But in general, you will see 15 decimal places, whether this is for small numbers or, very big numbers. Oh, let's get bigger than that. We'll switch into scientific notation eventually. You still get 15 significant figures times 10 to the 28th power. And somebody wanted to try what happens if we then square it using the square operator instead of multiplying by the same expression again, still get the same error. Okay. Great questions all. Key takeaways. There are two different types of real numbers, an integer of any size or a float. The float has a number with an optional fractional part. Sometimes you get a float that's just 10.0. It's still a float because it has that decimal point when you display it. An int never has a decimal point. A float always does. A float might be printed using scientific notation. That's the E. And there are limitations to float values. There's actually a maximum float value, the biggest possible one that can be represented, but it's so huge that you probably will never hit it. But the important one is that they have limited precision, 15 or 16 decimal places. So if you want to represent something even more precisely than that, then the kind of built-in number representations in Python are not what you want. One more question. What happens when you have a number with more than 16 digits before the decimal place? You still only get 16 significant figures. So if I have some big number with 18 digits, and then I say 0.0, we're going to lose a little bit at the end. We lost the 9. And someone asked, what's the reason behind 15? It has to do with how computers actually represent these, which is as ones and zeros, as bits. You can learn exactly how the representation works if you want by looking up the standard or by taking CS61C. It will not improve your life at all to know how it works if what you want to do is perform data science. So that's why we don't teach it in this class, is like, how do we represent it in bits? Well, it's clever, but it doesn't actually matter unless you're building a system. But if you're just using this as a tool, what you need to know is that there's this limit, and it has to do with the amount of memory that's allocated in order to store a number. And that's a fixed amount, whether it's 2.0 or 200.0, you still use the same amount of memory, and that memory is finite, and that finite memory gives you 15 or 16 significant digits. Sometimes you get 17, but like exactly how many doesn't matter that much. Just remember it's around 15 or 16. Okay. Strings. They hold text. We talked about that last time. There were some questions, so I figured I'd try to address them. So here's a string that's different from a name. If you evaluate anything in quotes, you're going to see that in quotes, whereas a name evaluates to its value, which had to be set using an assignment statement. And since there was never a flavor equals anything assignment statement, if I try to evaluate flavor without quotes, I get a name error. You can pretty much put whatever you want. Spaces are fine, capitals are fine, numbers are fine. The only thing you can't really put in there is another apostrophe. Because look, you can see it in kind of the coloration. Even though I meant this as part of the word don't, Python's interpreting it as the end of the string. So it's giving me a syntax error that doesn't know what to do with this T, because I wrote a string Don and then I put a T there. There's a simple way to fix this, which is that you have the option to use double quotes instead of single quotes. And within a double quoted string, you can have apostrophes. Within a single quoted string, you can have quotation marks. And that's the end of the story of what's different between double quoted strings and single quoted strings, is that if you need an apostrophe in there, then use double quotes. If you need a quotation mark in there, then use single quotes. If you need both, then you have to do this thing called escaping, which I'm not going to teach you about because it's kind of esoteric, but there's a way. But usually you don't need both. So now you know the difference between single quotes and double quotes. You get the same kind of thing in the end. I know this looks like it's different than this because it has double quotes around it and this has single quotes, but in fact, they're both just strings. Same kind of representation under the hood, same set of things you can do with them. The only difference is that since this one has an apostrophe in it, Python shows it with double quotes so that you know that if you copied this and you pasted it in again, it would work. Okay. A great question is, what is a string? String is just the jargon that we use to say a representation of text. Why is it called a string instead of text? Well, you might not have text, you might have numbers in there. So strings are pretty flexible. You can kind of put any characters that you want. So someone invented this term string. And it stopped. Someone asked, what if you put a quotation mark in a quoted string? Then you have a problem because we have Python thought this was the end of the string and then I didn't know what to do with this word quoted. What are strings used for? They're to represent text. So it might be the case that we want to run some analysis, not over a column of numbers, but a column of names of basketball players or something like that. And yeah, so we use strings to represent each name. You do not need to use assignment in order to create a string. But I am allowed to assign string as a value to some name. What I've done here is I've introduced the name hi and assigned it to a value hello, and now I can talk about hello. You can even manipulate strings. I could say hello students. The addition operation, when performed on strings, creates an even longer string that concatenates together the first string and the second string. Notice that it doesn't give you a space automatically, which you might think is annoying, but you can add the space there yourself. You have full control. You could even add a third string in there that just contained a space. So there's a little string that contains the space. And since we've added all three of these together, now we have a long string hello space students, which is the concatenation of the contents of this, the contents of this, and the contents of this. Even if I have a variable name that is bound to the string, I can do the same kind of thing. So hi plus students, I'm going to slip a space in right there, will not show me hi students, but hello students, because hi is a name bound to hello, and hello is the value that we're adding to students. What else can I tell you about strings? You kind of heard it. There's this funny behavior you'll rarely use, that you can multiply a string by an integer, but you can't multiply a string by a string. And Python just doesn't know what to do with that. And it tells you directly, can't multiply a non-integer by a string, because it just doesn't know what that means, even though you could add these together. There's one more bit I wanted to show you, which is about types. There are two built-in functions, well, three built-in functions that convert to and from strings and numbers. So what if you have a string and you want a number, you have a number and you want a string? Well, if I have the number 3, I could get a string that contains the digits of the number 3, just like that. Why is this useful? Well, if I wanted to build a long string, my kid is 5, that's not going to work because it's going to tell me I don't know how to put together a string and a number. But if I turn this into a string, then it works. What happened there? I built a string containing the digit 5. I added that to a string containing my kid is, and now I have a string my kid is 5. You can go backwards too. if I have a string 23 and I want to get a number for it so I can add 1 to it, then I would just call int on it. Now it finds an integer which is equal to the digits 2 and 3, and now that's the number 23, and I can add 1 to it and get 24. There's also a float function which will interpret a string that contains a decimal point. Now it has to be a well-formed number. If I say 23.45.67, like that's not a number, and so it will say it can't convert that to a float. But if you have something that looks like a well-formed number, it just happens to be a string, you can turn it into a number. You might wonder what happens if I try to turn this into an int. Invalid literal for int with base 10, 23.45. Just means this is not an integer because it has a decimal point. Part of learning the program is to ask, like, what if I combine these in weird ways? Like you just told me that float takes a string and turns it into a number, but what if I pass in a number? What does it do? Well, it still works, turns it into a number. And int, takes a string and turns it into a number. Well, what if I pass in a float? Well, actually, int does something a little bit different. Instead of interpreting the string as an integer, it finds an integer that's near to the floating point value, and it happens to round down. So you just have to be aware of the functions that I tell you about might have interesting behavior. I try to tell you about most of it, but in order to really remember it, you're going to have to try some of this stuff out yourself. That's what lab is for. But I would encourage you to just mess around on your own too. There's a request for a lesson about string formatting. I think it won't fit in today's lecture, but I will add it to a future lecture. Thank you for the suggestion. If you assigned a value to a string and then multiply that string, would it work? So if I said x equals half, and then I wanted to be really funny, would that work? And yes, it would. Hilarious. I'm looking for questions that I can answer. Great questions all around. I answered a few of them. Someone asked, are there real applications for typing out strings this way? Yes, we're going to see lots of them in the course. So instead of trying to give you one now, I'll just say, I'm only teaching you stuff that's really essential to do interesting applications. Well, except for the multiplying strings. That's kind of like not particularly useful, but it has come up a few times in my life. So now you know about it. A string value is a snippet of text of any length. A word, or a whole sentence, 2 sentences, anything's fine. Strings consist of numbers. If you have a string which just contains digits, then you can convert it to an integer. If you have one with a decimal point, you can convert it to a float. Any value can be converted to a string just by calling stir on it, and this works and never breaks. It always gives you some kind of string. Strings that contain numbers can be converted to numbers, which is actually quite useful. But it has to be in the format that Python accepts, which is digits with a decimal point. And it's also the case that numbers can be converted to other numeric types. So you could turn a 1 into a float. I don't think we did that one. Let's do that really quick. Float 1 gives you a floating point representation of the number 1. 15 significant digits, but since only one of them is non-zero, you just see the 1.0. If you convert something to an int that was a float, then you're losing the decimal portion. All right, so if we had assigned x to 3, y to the string containing 4, and c to the string containing 5.6, what is the source of error in each example? Let's do these together because you can't talk to the person next to you because we're not in a lecture hall yet. So if you add the number 3 to the string 4, you'll get an error that says incompatible types. You can't add a number to a string. If you add a number to an integer, that part's fine, but let's see about converting y plus z to an integer. Well, what is y plus z? It's a string containing 45.6. Because the plus here is adding two strings together, which concatenates them. 45.6 is not an integer. So when you try to convert that to an integer, you'll get an error that says, this is not an integer. What if you turn x to a string? Well, then you have the string containing 3 and add that to an integer 4. It's very much like a. You can't add an integer and a string together. You can add two integers and you'll get a bigger number. You can add two strings and then you'll get the concatenation of both strings, but you can't add a string and an integer. And what about y, a string added to float z? Well, actually float z will work fine. It will give you the number 5.6, which is a floating point number. You add that to a string and now you have a problem. String plus a number gives you an error. A few more demos. Then we're going to do arrays. There's a built-in function called type. You use it in order to see what's going on. Now, of course, the type of 10 is an integer. That's like not very interesting news. But if I had set x to 10, and then I had done a bunch of work, and then way down here, I wanted to know what sort of thing is x anyway, this might be particularly useful information. Type doesn't tell you that this is a variable. It only tells you the type of the value that this variable name x is bound to. So what's happening here is that x is bound to 10 because we set it long ago, and we're figuring out what type of thing 10 is. The type of 4.5 is a float. The type of 1.0 is a float, even though this is also an integer. What type is telling you is how Python is representing the number. Not in essence, what kind of number is this, but how is it being represented? Is it represented as an integer, which can be arbitrarily large and full precision, or is it represented as a float with finite precision? Type of hello is a str, which is a string. What else is there? If we load up data science, and we read the table of NBA salaries, this is a value. It has a type. What sort of type is it? It's a table. It's a data science table's table type. This is basically just telling you some hierarchy of where this is stored in Python's environment. But this part doesn't matter so much as the end, which tells you what kind of thing it is. It's a table. Oh, there's one other kind of thing we've seen. There's functions. This function called abs, in fact, has a type. Built-in function or method. Okay, just like something interesting. So we've seen ints, we've seen floats, we've seen strings, we've seen functions, which we'll talk about a little bit more later in the course. We've seen tables. There's another type we're about to get to called the array, and it's an important one. Type can tell you the type of a value. Even if you have a large expression, it's going to compute the value of that expression, then tell you the type of it. And here we saw, if you type x, it's not going to tell you x is a variable. It's going to tell you the type of what x is bound to, which is the number 2. Don't see any questions about type. So now we get to talk about arrays. Arrays have lots of applications. The first 4 integers are 1, 2, 3, 4. First 4 is a name that refers to all 4 numbers at the same time. It's an array of numbers. And what's this NumPy thing? Well, this is one of the most popular modules in all of Python. It's a numerical computing module that's used pervasively across all sorts of different applications to represent arrays of numbers. It's basically what it does. And it's got built-in operations on those arrays of numbers. And the top of every single notebook, including this one, we're going to import NumPy. It's so popular that it's got a standard abbreviation, NP. And the reason that you might want that is that when you have an array, you can perform NumPy operations on it, like averaging the first four numbers, which gives you the average of 1, 2, 3, and 4 is 2.5. And you see all the different things that NumPy does. Yes, I just hit tab. You can see this huge long list. I'm not going to go through it now. You should not memorize all of them, but you might one day want to explore a little bit. I would not do it this way, but instead I would go to the website about NumPy and read the documentation there. It's much more useful than going through this long list. But I did want to show you that there is quite a bit you can do with an array, and it's all there, hidden behind things like np.average, np.sum them up, etc. So one interesting thing is you can give a name to a whole list of numbers. The second interesting thing is that you can perform arithmetic on all the numbers at once. This adds 3 to each of the numbers in the first 4 array. This multiplies each of the numbers by 2. This is the way in which tables or columns of numbers are manipulated in Python, is to put them all in an array and then perform some arithmetic like this. There's 2 kinds. Either you want to do exactly the same operation to each element, and then you just write times 2, or you could even square them all if you wanted. And the other kind is that you want to combine pairs of numbers in 2 equal length arrays. So if I have 5, 6, 7, 8, I can add the first 4 to the second 4, and I will get, what happened here? We had the first 4 is 1, 2, 3, 4. Second 4 was 5, 6, 7, 8. We got 1 plus 5, 2 plus 6, 3 plus 7, and 4 plus 8 as the 4 different results. If I only have 3 numbers and I try to add the first 4 to only 3, then I get an error. You can't do the matching up process unless they're the same length. So things you do with arrays are you either manipulate each element in the same way by multiplying by 2, for example, or you take 2 arrays of equal length and then you can combine them. And you can combine them however you want. Not sure what I did there. So you can take the first 4 and multiply them by the second 4. That takes the first element of this, the first element of that, multiplies them together. So the 1 times the 5, and then the 2 times the 6. Here's the 2 numbers. 1 times the 5, 2 times the 6 is 12, 3 times the 7 is 21, 4 times the 8 is 32. That's what we got. Now there must be some questions. NP is an abbreviation for NumPy, which is the module in Python that stores all of the interesting functions that you can call on arrays. How come you can't just type .average? You have to type numpy.average. It's just how Python works. But the average function is bundled together with a bunch of other functions in the NumPy module, which we refer to as NP. And so we have to say NP dot, and then the thing that we want to do. Most interesting functions that are built into Python are part of a module, and so you have to access them like that. What's an array? An array is a list of numbers. It's in fact a list of values that all have the same type. So it is possible to make an array out of strings. It's just, it's harder to do anything with that array, but we'll encounter them regularly. We could figure out how long it is. So if we say this is a bunch of strings, we could figure out how many elements it has. There are other things you can do with any array, whether it has numbers or strings in it. You can figure out its length. You can also get a particular item within it. And here's the syntax to do that. Pass in any integer smaller than its length, greater than or equal to 0, and it will give you the corresponding element. And this same syntax of dot item 0 will work on this array of strings. It will also work on this array of numbers that we made earlier. I think you get the idea. You might wonder what happens if I get the 7th item in this 4-element thing. We get an error. So there's only 4 elements. You refer to them as 0, 1, 2, and 3. Why do you start with 0, you might wonder? You should think of this as the offset from the beginning. So 0 more than the beginning is the very beginning, is the element at the beginning. The reason that it's indexed this way is due to some decisions that were made when the programming language was created. There's reasonable justification for them, but at this point in your life, you should just memorize that the beginning is 0. That's 0 offset from the beginning, and this is 1 more than the beginning, is the second element. The question is, will we be using arrays exclusively in this course? Not quite, but we'll use a lot of arrays in this course. Mastering how to work with arrays is a central goal of this course in terms of the programming content, because it lets you do all kinds of interesting statistical inference. Oh my gosh, I'm over time. Okay, I'm going to stop. I'll tell you more next time. Thank you very much.